So let me start by describing our model for non-interactive MPC, at least the basic setting of this model. So we have n players, P1 up to Pn. Each player, Pi, as usual, has input xi, and they wish to compute some function f of these inputs. Non-interactivity, what we want is for each player Pi to send a single message based on its input to a special output player, which we call sometimes the referee, and denoted P0. So these are non-interactive protocols. Well, if you think about this for a second, you'll find out that you cannot do much in terms of security in such a model. If the function depends at all on EXI, then P0 will be able to find what is the EXI just by simulating messages from all other parties on a sensitive assignment. So this model, as is, cannot get us much. So we just add to it one ingredient, which is correlated randomness. So each player now has also a random input Ri, where the inputs R1 up to Rn are chosen according to some joint probability distribution R. So now you see that the previous attack fails. The PFS cannot simulate the players because it doesn't know their share of the correlated randomness. So this is good. Still, there is some some issue that is left here, and is the following. So we still want a non-interactive kind of a protocol. So one message from Pi, depending on Xi and Ri, to P0. That's it. If you look what a coalition that consists of P0 and some set of players T can learn in this situation, they can learn not just the value of the function f at point x, which is what they are supposed to learn, but also the value of the function on all other points x prime that are similar to x on all inputs outside of t, but maybe different on inputs of t. This is because players in t, because of the non-interactive nature of the model, can just try what will happen if we change our input to something else and see what's going on. So just to make it a concrete example, think about voting or majority as our function. So now players in T together with P0, they can see what happens if they plug as their inputs all zeros, and then a single one, and two ones, and up to ones to all of them. And so if the sum of the players outside of T is somewhere between n over 2 minus T to n over 2, they will learn what is the sum in the place that the value of the function changes. Okay? So this is unavoidable in this model. And so we'll call such a protocol capital T robust if this is the only thing that these players can do. And we'll call it little t robust if the protocol is robust for all sets of size at most t, and fully robust if it's robust for t equals n. And the focus in this talk will be on the case of semi-honest adversary and information theoretic security. Let me just mention some remarks and extensions for this model. So one thing is that we'll be interested in the case that we are not only computing a single function f, but want to compute a function f from a class of functions and keeping the actual function secret. We'll see why this is interesting, but this will be one of our goals. We'll also be interested in the more natural maybe model where all players want to have output. So the non-interactive setting, this would mean that each player sends a single message to each other player independently, and then they need to compute the value of the function. At least in the semi-honest case, it's easy to see that you can obtain such a protocol by just invoking n times the basic setting that I described in the previous slide. Okay. Also, of course, we should be interested in the case of malicious adversary. In this case, you first need to define what the malicious players can do in the ideal model just to handle the point of rushing, and then you can deal with it by standard methods. Note that because the protocols are non-interactive, What malicious players can do in terms of privacy is basically nothing over what they can do in the semi-honest case, because they don't get any interaction to play with. So it's mainly an issue of correctness rather than anything else. And OK, correlated randomness, I guess after the previous talk, maybe I shouldn't motivate it too much. Just wanted to say that it is used in many places. The simplest form of correlated randomness is the common random string, but more involved forms exist in other works, in particular in the previous talk. So just to formulate the notion a little bit, so non-interactive MPC for a class of functions f consists of a joint probability distribution R sub f that depends on the actual function that we want to compute, gives randomness to all players, and encoding functions for each of the players that compute a message based on the input and the random input. And as usual, we want a correctness, meaning that from the messages, you'll be able to recover the value of the function on point x1 and xn. And the T robustness, repeating what I said before, but a bit more formally, we want to say that the view of P0 and the players in T, that means that the messages that are coming from players outside of T, together with the randomness of players in T, doesn't give more information about the inputs of players not in T than would an Oracle access to the function restricted on those inputs. Okay? So this is just to have some definition in mind. OK, a little bit of motivation. So an obvious observation, you can look at the case of zero robustness. Zero robustness means just robustness against the referee itself. This is just the private simultaneous message model of Fege, Killian, and Naor, which is interesting by its own and also used as a building block in other protocols, especially protocols where you want to save on rounds. And in general, of course, if we talk about non-interactive protocols, this is part of a general large body of work that tries to reduce interaction in multi-party computation. Maybe one notable recent example is the model of Alevi, Lindell, and Pincus, where they try to eliminate all forms of simultaneous interaction. But compared to them, for example, we really want to be completely non-interactive. More motivation is the connection between non-interactive MPC and other primitives. So obfuscation is recently in the news, as we know. So just informally, obfuscation, even though we saw defined it a lot of time in this conference, is a randomized mapping that takes a circuit C from some class capital C and map it to another circuit C prime that is functionally equivalent to it. So one can show, and similar results were shown in context of multi-input functional encryption that I'll mention in a second, that non-interactive MPC implies obfuscation. And the idea is just to use non-interactive MPC for the universal function of the class C. So obfuscation, in a sense, you want to play with the inputs and don't want to play with the function. So this is similar to what's going on in the case of robustness. However, non-interactive MPC is different from obfuscation. In fact, achieving non-interactive MPC is non-trivial in some cases where obfuscation is trivial. For example, when you have just a single function, or when the functions are learnable, and so on. What we get in particular from this connection is that we can use the negative results that are already known for obfuscation and apply them to get negative results for non-interactive MPC. So for example, results of Goldwasser and Rothblum for obfuscation tell us that there is no efficient, fully robust information theoretic non-interactive MPC or NC1, in fact, even smaller classes, unless the polynomial hierarchy collapses. another thing that I wanted to mention is the connection with multi-input functional encryption. Again, not very formally, functional encryption first is an encryption that allows for every function f in the class capital F to produce a secret key that will allow to open just the value f of x based on the encryption and no other information about x. Multi-input functional encryption is a very strong primitive. It allows a similar thing, but f in this case can be applied to more than one ciphertext. So this is multi-input functional encryption. Multi-input functional encryption implies non-interactive NPC. It's easy to see, and in fact, it's much better in the sense that it is reusable. You can use it again and again. From recent results about multi-input functional encryption, in particular, the work of Goldwasser and others that show how to construct it from indistinguishability obfuscation, together with a candidate for indistinguishability obfuscation of Garg et al., we get a computationally secure, fully robust, non-interactive MPC under those strong assumptions that are used here to construct the obfuscation. In our case, if you give up on the reusability and allow to use correlated randomness, you can get a non-interactive MPC also in the information theoretic case. And in particular, there is the hope that such solutions will be much more efficient because they don't need all these assumptions that are currently used there. OK, so with all this, here are our main results. On the positive side, we show fully robust protocols for all functions f, where the communication depends on the size of the input domain. Unfortunately, not the representation of the input, the size of the input domain. So this can be considered efficient only if the function is small, not too many players, not too big inputs, but still maybe surprising. We show a fully robust, efficient protocol for group products, for all groups, both Abelian and not. This is sometimes very useful. And we show for the case of symmetric functions that include, for example, the majority function that I mentioned before, T-robust protocols with communication that is n to the T or order of T. So here again, if T is small, this may be efficient. Otherwise, maybe not. On the negative side, we just consider the previous solutions for PSM protocols and also garbling protocols, and we show essentially that almost all of them fail to give even one robustness. So if you, for example, in the case of garbled circuits, if you give two keys of the same gate, everything collapses. A notable exception for the last statement is Kilian's protocol for group products that we actually use in our second result with an appropriate analysis that you need to do. So in the rest of the time that I have, I want to show you some protocols as much as time will permit. So let's start with a very simple one. So this is a protocol for sum over any abelian group. So the goal here, a player PI has some input xi in the group. What we want is for P0 to compute the sum of these inputs. So here in the preprocessing, we simply choose n elements of the group at random, subject to the constraint that their sum is 0, and give Ri to Pi. And in the protocol itself, Pi just sum xi with Ri, send this as a message mi to P0, and P0 sums up all the mi's. Since the sum of the Ri's is 0, this will cancel out, and they will get the sum of xi, so correctness immediately follows. And the robustness, full robustness, follows just from the way that we chose the randomness. Okay, so it's very simple, but might be useful to remember. So let's go to another example. This one is more complicated. I'll give mostly the high-level ideas, but it's almost all here. So I want to show you a protocol that's fully robust for all functions. So I'll do it in the 2 steps. In the first step, I will show a fully robust protocol just for the following restricted class of functions, capital H. It consists of all the point functions HA. So HA gives 1 only if the input xi equals a, otherwise it's 0, together with the all 0 function. Okay? That's the choice of H. It will be clear why I chose it in the next step. So again, the input is xi. Say it's a bit. It can be other things. And the goal is for P0 to learn h of x. And it's important in this particular case that h itself will remain hidden. So P0 will know h of x, but will not know h. So here, the preprocessing does something a bit more tricky. So we pick 2n random vectors, 1 per each player per each input. So these are the 2n vectors. They are binary vectors of appropriate length, say 2n. If the function is the 0 function, these random vectors are chosen in a way that there is no linear dependencies between them. While if the function is the point function HA, there is only 1 linear dependency, and this is the one that if you sum up the bits, the random strings corresponding to the bits of A, this will sum up to zeros. Any other set of vectors is linearly independent, and Pi gets the 2 vectors corresponding to it, Ri0 and Ri1. And now in the protocol itself is simple. Pi just sends the message, as a message, the random string corresponding to its input to P0, and what P0 does, it just checks whether these messages are linearly dependent or not. Okay? And if they are dependent, he outputs 1. So in the case of the all 0 functions, no combination of strings is linearly dependent, because this is the way that we chose it. In the case of the singleton functions, there is only 1 combination that will lead to dependent vectors, and this is if x equals a. So this gives the correctness. The robustness should be argued a little bit, but there is nothing too complicated going on. I'll skip this argument. So this is the first step. So just remember, we have a fully robust non-interactive MPC for h that hides the function. So here comes the second step that will build on it. So the first idea would be to represent the function f just as the sum of all singleton functions corresponding to a's where f of a is 1. And then use the previous protocol to evaluate all these h's. Well, this doesn't quite work for 2 reasons. So first, you can see, for example, that we learn what is the number of 1s in f, and if we want to keep f hidden, this will not do it. But even if we don't care revealing f, it will tell us more than that, which is the a that is actually giving the 1. So this is bad for us. But these 2 things can be fixed in a not so complicated way. So the first thing to do is to write f a little bit differently as the sum over all possible a's of the function ha prime, where ha prime is the all 0 functions in the case that fa is 0, and it's the singleton function in the case that fa is 1. So clearly this identity holds. And so this immediately solves also the first problem. And then we randomly permute the order that we evaluate the functions. This is just done in the preprocessing stage by permuting randomly the randomness that is given. Okay? And if you do this, this immediately gives a protocol that is fully robust for the function f, any function f, and keeps it private. Okay? So that's the idea. I see that I am running out of time, so let me skip this example and just get to the summary. So we introduced the notion of robust, non-interactive MPC, which we view as both interesting on its own and as various connections to other primitives. We present various protocols for various classes of functions, and natural open problems or next steps will be to get protocols for other classes or to improve the complexity. Thank you.